Beautiful, isn't it? This painting was regarded in its day as one of the most accurate and elaborate studies of nature ever made. In my mind, an equation can be just as beautiful. Instead of paint and canvas, a mathematician uses numbers and equations to depict everything from the movement of atoms to the formation of galaxies. Mathematics can be used to view the world in a way that is as breathtaking as a Van Gogh, Monet or Renoir. The universe is literally painted with numbers. Have you ever counted the number of petals on a flower? Given the variety of different flowers in the garden, you might think that any number of petals was possible. But it turns out that many flowers like just 5 petals. And if it isn't 5, then they seem to favour other numbers, like 8, 13, 21. Perhaps you can see a connection between all of these numbers. You get each number by adding the 2 previous numbers together. So for example, 8 plus 13 gives you 21. These are called the Fibonacci numbers, and they're nature's favourite numbers. You find them all over the natural world. Take an apple, for example. Cut it in half, and you'll find 5 seeds at the centre of the apple. Count the number of spirals on a pine cone or on a pineapple, and you'll find 2 sequential Fibonacci numbers, say 8 and 13. Plant growth seems to obey mathematical rules. But it's not just flowers that like these remarkable numbers. Snails build their shells in very much the same way as the Fibonacci numbers are built. A baby snail starts off with a tiny shell, kind of 1 by 1 square house. As the snail outgrows its shell, it adds another room to the house. As it continues to grow, it adds more and more rooms. But since it hasn't got too much to go on, it uses the dimensions of the 2 previous rooms to build the next room in the house. Just like the Fibonacci numbers are built out of the 2 previous numbers in the sequence. The effect of this growth is to produce a beautiful but simple spiral. Just an example of how mathematical patterns are fundamental to nature. Charles Darwin described the honeycomb as a masterpiece of engineering that is absolutely perfect in economising labour and wax. The honeycomb is made from tiny slivers of wax. A bee has to eat about 15 times the amount of honey for every bit of wax it produces. So it makes sense for bees to build their honeycomb in a way that produces the most storage space with the least use of energy and materials. There are countless different shapes the bee could have used to build its honeycomb. So why does it always choose hexagons? This is a question which has fascinated generations of mathematicians and scientists. Despite centuries of calculating away, no mathematician could beat the hexagons of the honeybee. But it was only recently, at the end of the 20th century, that an American mathematician called Thomas Hales finally proved the honeycomb conjecture, that the best way to cover a surface with equal area and the least perimeter is to use the hexagons of the bee. Mathematics lies at the heart of the perfection of the honeycomb. It's also key to many of the other things we consider beautiful. I love music, both listening to it and playing it. I actually listen to a lot of music whilst I'm doing my mathematics. For me, the aesthetics of a musical composition have a lot in common with the best pieces of mathematics. Where themes are established, they mutate and interweave until we find ourselves transformed at the end of the piece to a new place. Just as I listen to a piece of music over and over again, finding resonances that I missed on first listening, I often get the same pleasure in rereading proofs, noticing the subtle nuances that make the piece hang together so beautifully. Sometimes mathematics at school feels like a musician learning their scales and arpeggios, and we never play students any real mathematical music. Although it takes years of training to be able to compose the great mathematical works, even with the maths we learn at school, it's still possible to hear some of the beautiful music of mathematics. The connection between mathematics and music isn't just their beauty. Numbers actually play a part in explaining why we find certain notes harmonious and others dissonant, a discovery made by Pythagoras, he of right-angled triangle fame. He was passing by a blacksmith one day when he heard the anvils being banged. He was struck by how the notes sounded in perfect harmony. When Pythagoras investigated, he discovered that the weights of the anvils were in whole number ratios to each other, and he thought that these numbers might have something to do with why the notes sounded so harmonious. Experimenting with a stringed instrument, Pythagoras was able to confirm his hunch that there was some connection between whole numbers and harmony. Let me show you how. If you play a note on an open string, and then you halve the length of the string, I get a note which sounds almost the same as the first one, just higher. We call this the octave. Now play a note which is a third the length of the string. You get a note which is in harmony with the previous two. These whole number ratios of strings seem to be the key to creating notes in harmony. Pythagoras was so excited by his discovery that he thought the whole universe was built out of numbers. I asked physicist Mark Miodownik what he thought of Pythagoras' idea. Hi Mark, good to see you. So, was Pythagoras right when he said that mathematics is the key to the universe?
Well, let's think about this. Perhaps let's pretend that the head on my pint is the universe and yours is another universe, and they're very different actually, aren't they? And if you want to understand this universe, would we have to understand different physics? Or actually, is the physics of foams common in both cases? And if so, can we explain what the difference between these two foams is?
Right, because this one looks much thicker than my one,
yeah.
So there's obviously some different things going on in these two beers.
And this will last longer, we know that. I mean, the heads last right to the bottom of the pint. So, but it's still too complicated a question. Let's back up a bit. Maybe let's try a simpler thing. What are foams made of? They're sort of made of bubbles, right? So maybe we think about one bubble.
Right,
first.
yeah. I mean, that's a classic move for a mathematician, actually, to make this problem as simple as possible and see if you can solve that one first.
Yeah. So this isn't actually a glass of vodka I've got here. I haven't got a big drinking problem. Oh yeah. Anyway, so this is glycerine with detergent in it. So we can make some bubbles. I've got some little implements here. So if I just dip this in here, watch this. You must have seen that before.
Beautiful, and you get a beautiful sphere,
yeah,
one of mathematics' favourite objects.
Now, the question is, does it matter what I blow it through as to the shape I get? Like, the reason I get spherical bubbles, is it because I blew it through a circular wire?
Okay.
So here's a triangular wire.
So we're going to get a pyramid now.
Hopefully. Let's see if we can do it. Ah. So
okay.
The thing is, it doesn't really matter, it turns out, you can see this from experiment, what you blow the bubble through, you always get a sphere. So that's some really underlying physics, forcing it. You're forcing it into some shape, and it's forcing itself back. Okay. So what is that? And that turns out to be a competition between pressure and surface tension. And you can write an equation, a very simple equation for that. And it's pressure equals surface tension over r, where r is the radius of that sphere.
So can you use mathematics to control the world?
Right, so then we can manipulate it. So, for instance, we didn't really talk very much about gamma, the surface tension of this, or this. But in fact, if you change the surface tension, you'll change the stability of the bubble. So the reason we can blow big bubbles is because we have a very low surface tension liquid. So it's very low gamma. But if we were to increase gamma, we'd make it harder. So, for instance, if I was to increase suddenly the surface tension of your pint, all that foam would disappear.
Okay.
And you can do that through chemicals, right? So
okay, yeah.
I've got something over here which will change the surface tension of your, and it will just completely get rid of your foam.
Oh, yeah.
Sorry about that.
Is my beer drinkable now? It smells disgusting. What did you use?
Aftershave.
Oh, no. Well, I'm going to have to go and get another pint then.
Sorry, Mark.
Thanks, Mark. Mark's experiment with my beer just goes to show that Pythagoras' notion was right. We can describe virtually anything with numbers. One of the first people to realise the power of mathematical equations to describe the natural world was Galileo Galilei. He once famously wrote that the language of the universe is mathematics, and its letters are circles, triangles, and other geometric figures, without which means it is impossible to comprehend a single word. He once showed that objects of different sizes drop at the same rate, regardless of their weight. That is, provided you ignore things like air resistance. It was while experimenting with dropping objects that Galileo came up with the law that the distance the object has fallen is proportional to the square of the time of falling. In other words, or in mathematical symbols, d is equal to a times t squared, where d is the distance travelled, a is the acceleration, and t is the time it spent falling. This was one of the first examples of a mathematical equation to describe the natural world. But Galileo didn't stop there. That was a perfectly timed volley by Victor. His brain will have been subconsciously working away, calculating the flight of the ball, so he can time his foot to be in the right place at just the right time. This equation, another one of Galileo's, determines the height of the ball given its starting velocity when it was first kicked. Obviously, Victor needs to solve the quadratic equation to know where the ball is going to land so that he can volley it before it touches the ground. But there are some complications he needs to factor in. This second equation controls the drag factor on the ball, which changes the ball's velocity as it flies through the air. The smooth surface of the ball has a strange effect, causing the drag to be very small at first, then suddenly, towards the end of its flight, the drag suddenly kicks in, slowing the ball dramatically. It's quite counterintuitive, and it's caught out many a professional goalie. Having worked out the flight of the ball, Victor needs to solve the equations all over again to find the most efficient path from his foot to the goal, whilst avoiding any obstacles like defenders on the way. As the great Dennis Bergkamp once said, every kick of the ball requires a thought. Victor is probably unaware of all of these equations. It's one of the greatest achievements of our species that we can express how the world works using mathematics. It's something that has helped us to design better footballs and put a man on the moon. The beautiful way that mathematics is so perfectly threaded through the natural world provides some with a sense of the divine. Perhaps because, in the words of Bertrand Russell, mathematics constructs an ideal world where everything is perfect but true. Galileo thought that mathematics was the language of God. Whether they think there's a God or not, many scientists believe that if there is a rule book that tells us exactly how everything in the world works, it'll be written using mathematical equations. These equations are some of the most famous ever written. These ones tell us how electromagnetic waves behave. This equation over here describes the quantum process of entanglement. In my opinion, these are some of the greatest cultural achievements in our history. I consider myself lucky to be able to appreciate their beauty and elegance. I hope I have at least given you a glimpse of how the universe is indeed painted with numbers.